That'd be a cool project. Do we have everybody back?
Yes, we do.
Okay, lovely. Okay, so we have everybody back. So yeah, like if we had like more time, I'd love for us to just like discuss and like share from like all like the different rooms. I saw a lot of great discussion between people. But just to like keep things moving, I'm gonna just launch into the presentation. And if you want to see like the full list, like the full like list of like correct answers, I posted something on the last slide for resources. Does that sound good to everybody? Okay, great. And yes, I'm going to present, and I think this is going to make it hard for me to see people's faces. So if you have a question, please let me know. Great. Okay, so I'm going to share that. Do people see it? Great. And now I'm going to play. Right. So last lecture, Ryan was telling us the bad news about C and C++, all sorts of issues with memory safety that lead to even security vulnerabilities and just like broader issues with correctness and stuff like that, right? And this lecture, I'm going to tell you about how Rust is going to try to address some of these issues. Now, that being said, as a disclaimer, you can still write buggy programs in Rust, okay? Like, by all means, like this is a great like exercise, I guess. I mean, I don't know, like if it's like a good exercise, just like write buggy programs. But there are ways you can screw up in Rust, okay? Like all sorts of logical errors and stuff like that can lead to all sorts of issues, right? But Rust just makes it harder to make certain kinds of mistakes. And we'll see what that looks like concretely later. So let's first think about why it's so easy to screw up in C. So that was the whole point of the exercise that y'all just did in the discussions you've had. So we already did this. Let's talk about a couple of those errors. So the first class of error I'm going to talk about is something called the dangling pointer, right? So could someone just quickly explain what's wrong here? Just feel free to chime in. Anyone? Okay, great. So we have an invalid pointer. Is there something wrong with that? Could something bad happen? Like why, what's like what do you think could go wrong? Yeah, it's going to clobber whatever is at that value. So if you put some like interesting things in your array that you hoped would be there later on, the bad news because it's all deallocated and it's going to get overwritten with other stack frames, right? So that's really bad. Here's another one. A lot of you spotted this in your discussions, but there's a double free going on right here, which is not good. So, why is this bad? Yeah, totally. It's really just it's corrupting heap state, right? And a couple of you mentioned that you're taking CS 155 right now. This is not something that we're going to talk about in this class because it's beyond the scope of this class. But we can post resources to it if you're interested in learning more. And this is actually part of the first assignment in 155 is you'll learn how to take a double free and use it to like control hijack a program. This is actually a security vulnerability too. If you have questions about why that is, I probably don't have time to explain it right now, but please feel free to like talk to us after lecture and we can point you to some resources. But it's just cool to think about how like something that seems kind of innocuous, like a double free, can actually lead to something pretty drastic. And then now there's something that I think a couple of you mentioned in your groups as I was floating around. There's this iterator invalidation issue here. So could someone try to, I guess, like explain what's going on here or why this might be bad? Or like, why am I highlighting that particular line of code? I guess the issue is I'm not showing the full context. So if you have the full code snippet, make sure to look at what that push is doing. Exactly. That's a perfect explanation. So n is now pointing to freed memory, and right, like it's pointing to something that's no longer valid. It's sort of like, I think this is really, you can think of this as like a trust issue in a way. Like I thought n was going to point to this vector. I thought it was going to point to some valid memory, and it just changed under my nose, right? Like I thought it was something and it ended up turning into something else. So it's sort of like, this is definitely something bad and something that will lead to like unexpected behavior, right? Um, and here's another one right here. We have a memory leak, right? We forgot to free the old data, right? So this is under the circumstances in which we uh, need to like resize our array. We need to create a new array, copy over what was in the previous array to the new array, and have that be like our current working array. But we forgot to free the old memory. So this is pretty bad, right? And this kind of goes back to something that Ryan was talking about last lecture. It is incredibly hard to reason about programs. Sometimes it's impossible, and sometimes it's even more than impossible. I'm not going to talk too much about what I mean by that, but if you're interested, you should take something like CS 103 or CS 154. So like Ryan mentioned last lecture, if you give me a program and you claim like this program will eventually stop, right? This program will halt. This is something called the halting problem, right? It's in general like computationally impossible to prove that in the general case for certain technical reasons. And this is actually a really old result in computer science. Some might even say this is the oldest result in computer science. This is something that Alan Turing came up with, who's pictured on the right there. This is something he came up with almost 100 years ago, I think. I don't know the exact time scale, but yeah, so like this is something like this, we knew this before computers were even built, which is kind of crazy to think about. And what do I mean by more than impossible? Okay, so it turns out that there are problems that are even like harder than the halting problem. Like something like secure voting machines, right? Like if you give me a piece of code and you claim this is a secure voting machine, right? It's very like relevant to our election, right? You might have seen this in CS 103. It's impossible to prove that. It is literally impossible to prove statements like that in the general case, right? And now you might be wondering, okay, so like why do we care that it's hard to prove statements like that, given what I've told you about Rust? I guess, can someone kind of like see where I'm going with this or suggest? So we have a tool like Rust that wants to prevent us from making the errors that we saw before, right? Why might these results make us a little bit pessimistic about being able to do that? Any thoughts? Exactly, exactly. That's a great way of putting it. If it's hard to show any non-trivial fact about a program is true, how can I show facts like I'll never dereference a null pointer, or I'll never dereference a pointer to invalid memory, or I'll never do a double free? These are other kinds of like non-trivial properties of programs that are of the flavor of like, do I have a secure voting machine? Will this program halt? Stuff like this. And this is stuff that we want to be able to reason about during compile time. This is actually, I probably should have like mentioned this before. Rust is able to get you some of these it's able to resolve those kinds of errors that we were just talking about at compile time, which is a huge deal because it doesn't even need to run your program in order to understand if you're making those kinds of issues, right? So what's sort of the solution to this? I guess I sort of have it in that last bullet point, but like, what do people think? How do you think we can cope with this, right? How do you think we can cope with the fact that, you know, it's impossible in the general case to like prove interesting facts about programs? Okay, sure. So like simulations, like maybe this is of like, yeah, we can try to like see like what might our program do, like if we can just like reason about it by looking at the code. Um, any other ideas? Exactly, exactly, right? So the issue is like something like C. C is a very liberal language. You can kind of do whatever you want. That's why it's what's great about it, but also what's horrible about it. It's so easy to shoot yourself in the foot with C because like you can have like they can like type a random string and it'll probably like compile as a C program, right? Like that's awful, right? How like liberal the C compiler is with like what it does. But like Lake mentioned, if you add certain constraints to the kinds of programs you can write, that makes it harder to shoot yourself in the foot, and maybe you can get some guarantees out of that, right? So this is kind of like the art of like programming languages and PL theory and stuff like that. How can we add constraints to what we're allowed to express that enable us to have guarantees? Are there any questions about that? Yeah, this is like a super abstract idea, but we're going to see it more concretely in the case of Rust. But like, other than that, are there any like general questions right now? Okay, so moving forward. Yeah, so Rust, just like mentioned, needs to place restrictions on the program you can write. And unfortunately, this can make it difficult and maybe even sometimes impossible to write certain programs in Rust. A lot of y'all have been sort of like asking questions on the Slack, which is wonderful, but like there are like some like weird quirky things that Rust does with regards to like how you pass references around that make it hard to express certain things if you haven't seen like the full picture, right? And sometimes in systems programming, you need to be able to do sort of low level like manipulation on memory and stuff like that. And that by itself is just like an unsafe thing, right? So sometimes you need to break Rust safety guarantees in order to do everything you need to do. And in order to do that, you use this thing called the unsafe keyword, which we'll talk about later in the course. Don't worry about that for now. For now, we're only talking about safe Rust, okay? But you know, like under the hood, like even some of the things that you interact with in safe Rust have to use the unsafe keyword. It's just like that code is like properly vetted. Like if you're wondering, okay, like this seems counterintuitive, why would I want to allow, like I thought the whole point of this was to be secure, like why would I even want to allow unsafe at all, right? If you limit and control your use of unsafe to like small pieces of code that are easy to like reason about and understand, then this is okay. And it can only strictly be better than having your entire program be unsafe, like you would in C. Does that kind of make sense to people at like a high level conceptual level? Yeah, we're going to talk about this a little bit later in the course though. This is more of an advanced point. So another like interesting thing to like recognize is that a lot of the guarantees you get from Rust comes from the checks the compiler performs, right? Like what the compiler can reason about the code statically at rest, right? And sort of the reason it's able to perform those checks is because of the restrictions and limitations the language places on you, which is again super abstract. I promise we'll talk about this more concretely in a couple of slides. Just keeping an eye on time. And the other cool thing is that sometimes Rust can exceed the performance of C because of the compiler optimizations it performs. And sometimes it can do these compiler optimizations because of the way the language is structured. And if you're interested in learning more about those topics, there are a bunch of great classes like CS 242, which is an incredible class taught by Will Crichton that also covers Rust in more of like a PL theory kind of way. And also CS 143, which is compilers, which I think is offered this quarter. You may or may not be taking it. Those topics, and as well as their follow-ons, right? I think there's like an compiler optimizations class. I think it's 243. So like these topics are outside of the scope of 110L, but like let us know if you want us to point you to resources if you want to learn more about them. This actually, I think like this is like a really open area of research, right? Like what kinds of like compiler optimizations can you perform, and how do you make sure that your compiler optimizations are correct, right? Because it's a long history of like we try to make something faster and it ends up breaking correctness. Yeah. Are there any questions so far about anything I've said? Okay, yeah. Continuing. Okay, let's go back to these errors that we were seeing before. And like, let's look back at the string link pointers thing, right? So like, wouldn't it be nice if like the compiler just realized that this vec piece of data just lives within those two curly braces, and we shouldn't return an address to it that escapes that lifetime in a way, right? Like, wouldn't it be nice if it was able to just sort of automatically figure that out? Or if we could like sort of like place a restriction in such a way, right? Furthermore, like with like this double free, wouldn't it be nice if the compiler said that once you pass a pointer to free, you can no longer use that pointer? So you know, in like something like C, like you might free a pointer and then you might set it equal to malloc of something else. But wouldn't it just be nice if like the compiler said, you just freed this pointer, like just don't use it anymore, right? Like call it something else maybe, right? But you don't want to be able to sort of like run into this issue where you like double free something, or you end up using a freed pointer, right? Or you try to dereference a free pointer, right? And furthermore, wouldn't it be nice if the compiler stopped you from trying to modify this data that n was pointing to, right? So like vec push will modify the data that n is pointing to, like kind of like right under our noses, right? Wouldn't it be nice if the compiler recognized, okay, you actually have a reference to this piece of data. You shouldn't be allowed, like we shouldn't have someone else like vec push change that data while we still have a reference to it, because we might try to use that reference later. In fact, we do use that reference later. We use that reference in printf. These are sort of things that you can see by looking at the code and not even having to run it, right? These are things you can reason about at compile time. So these are sort of like the high level ideas behind ownership and borrowing, which we're going to see in just a little bit. And then furthermore, like with the memory leaks, right? Like, wouldn't it be nice if the compiler just realized that, you know, if there's no longer anything pointing to this heap chunk of memory, right, we can just get rid of it. We can free it. So we don't have to automatically insert those free calls ourselves. Yeah, great question. Would someone like to explain why this is an error? Maybe someone we haven't heard from yet. I heard a couple of people talking about this in the breakout rooms. Does that make sense? Yeah, why would it n point to the new memory, right? Okay. Right. No, but yeah, these are great questions. So, right. So now that we've like sort of built up, like I'd like for us to like take a pause, like maybe just like stand up in your seats, like do like a little stretch or something. I don't know, maybe like in a future lecture, I can like lead us through some like yoga. But it's important to, for the sake of your own sanity, to just sort of like get up, stretch around a little bit. Okay, great. I see a lot of stretching. And we only have 20 minutes left, so we're going to make this a brief stretch. But let's go forward. I guess like also during this pause, are there any other, this is an opportunity for people to ask questions about stuff. Are there any other questions people have? Okay, great. So let's continue. So let's think about how Rust might prevent us from making the errors that we just saw. So there's this concept called ownership in Rust. And a lot of y'all were actually running into this issue in the questions that you're asking on the Slack. So it's great that some of y'all started the assignment before this lecture, because you're already to see this, these things pop up in the compiler messages, right? So, you know, and I'll like show this in a code example more concretely later. But the idea is that, you know, each value in Rust, so think about it, each data chunk in Rust, each piece of data, each resource in Rust has a variable that's called the owner, and you can only have one owner at once. So some of y'all would have functions that would like try to like print a string in like some formatted way, for instance, and then you pass the string in as an owned value, right? And you're transferring ownership there. And that's why you'd run into a lot of the errors that you had before. There are ways we can get around that we're going to talk about in just a couple of slides, but this is why you saw those errors, right? And if you haven't started the assignment, you might start seeing the word ownership or like moved, like pop up in some of your compiler error messages. And furthermore, the idea is like when the owner goes out of scope, the value will be dropped. So by dropped, drop is just a name for the destructor, right? The thing that will get called once this resource needs to be deallocated. In the case of like a pointer to heap memory, right? This will be like freed, for instance, right? If this was a file, the file will be closed, and so on and so forth, right? So this idea is a very big idea in systems programming. It's often called RAII, or resource acquisition is initialization. I believe that's the acronym, which we won't like talk about in too much depth. But the idea here is that like, even though this is an idea that's unique to Rust, it's something that also exists in other languages like C++. Like C++ also has destructors, and it's something to be aware of. And yeah, this is exactly the point I wanted to make. It isn't like controlling references to resources isn't unique to Rust. If you're taking 110 concurrently with this class, you might have learned about the open file table and the fact that there's a ref count. And once the ref count in the open file table entry drops to 0, that entry is deallocated. Rust actually has a special kind of heap pointer that does the same exact thing with regards to reference counts. And this is an idea that pops up all over again in systems, because we want to make sure we're being smart about how we're managing our resources. We don't want our resources to be kept around longer than we need them. We want to be good citizens of our operating system, for instance, and we want to relinquish our resources as soon as we can. Does this high-level concept make sense? Great. So let's actually look at it in context. So one way you can transfer ownership is by making a variable assignment, right? So if we have this variable s, which is a string, and if I say, also this let syntax, if you haven't seen Rust syntax yet, let is how you declare variables. If I say let u is equal to s, that means I am transferring ownership of that string to u. And now when I try to print s, I get an error. What is the error I get? So the error is actually like really helpful. Like one of the things I love about Rust is its compiler. It's such a great compiler. It tells you exactly what's wrong, and it sometimes gives you suggestions about how to make it right. So it says that the move occurs because S has type string, which does not implement copy. We're not going to talk about copy yet. We'll talk about it in a couple of slides. But it's saying that, okay, you moved this string out of S and into U, and now you're trying to print S. This is bad. This is not okay. Because we don't know, because essentially like, you know, this S is sort of like, in a way, like a dangling pointer right now. Because remember, we want to have that property that there's only one owner at any one time. The owner used to be S, and then by that second line, the owner becomes U. So this is in order to sort of maintain that invariant that we want only one owner at one time. A way you might have seen this in your assignment, if you tried to decompose your code, was when you defined functions. I think a lot of you had questions about this. I got a bunch of different questions about this. So if you have this function omnomnom that takes an S string, like as an owned type, if I do omnomnom of S, so notice how we're just printing the string, right? Printing the string seems like an inherently safe thing to do. If I'm just printing a string, I'm not modifying it, it's fine, right? But what happens is that when you take, if you look at like that type signature there, because, let me see if I can actually do annotations. If I do, let's see. So like a pointer. Actually, I'm not going to try to figure that out.
We can see your mouse cursor.
Sorry. Okay. Yeah. Oh, you can see my mouse cursor. Okay. Great. Lovely. Yeah. So if you see this type signature here, it says S string. It means it's going to consume that string. That means ownership of the string is going to get transferred to this function omnomnom, right? Which we explain in the next slide, right? So when you move S into omnomnom, omnomnom becomes the owner of it, right? Technically, it's the parameter in the function that becomes the owner of it. But that means you can no longer use it in main. Are there any questions about this? This is sort of like the gist of ownership. I can imagine there are a lot of questions about this because this is a weird concept. I totally acknowledge, this is a weird concept that you probably have never seen in any of the programming languages you've studied. Great question, great question. So I can actually return S from the function omnomnom if I wanted to transfer ownership back. Does that make sense? Yeah, so it's like I give ownership to you and then I give it back to you. Like you can sort of like pass it around, like, you know, like you're borrowing a book or something like that, right?
Although we'll talk about the more common way to handle this issue in a couple slides.
Yes. Exactly, right. And then a caveat I want to mention is All right. Given what we just talked about, we have omnomnom is taking something called a U32. U32 looks like a weird combination of characters, but it stands for unsigned integer of 32 bits in length. That's what it means. And you'll notice I called omnomnom. So first of all, I said m is equal to n, and like that was fine. Like this code compiles, and you can see what it prints out, right? And then I said omnomnom of n, omnomnom of m, and then I was able to use them in the println afterwards. So how the heck is that possible? Like, why does it work differently with integers? I'm not going to talk about this too much in detail right now, but it turns out integers implement something called the copy trait, and that changes the semantics of this assignment operator, right? By semantics, I mean it changes what that single equal sign means. So when I say let m equals n, it no longer means transfer ownership of that integer to m. It means copy that integer to m. Does that make sense to everybody? So the way you want to think about this is there's a special subroutine defined somewhere that says, okay, every time I see an equal sign for integers, I'm actually going to treat it this way. I'm going to treat it by copying instead of by transferring ownership, instead of moving. Moving is the technical term for transferring ownership. Does that make sense to people? Are there any questions about that? Yes, okay, so the string case, it doesn't have, so like integers have a special subroutine written somewhere. There's actually something called a trait. There's something called the copy trait, and we're going to talk about that later in the course, probably a little bit next week. And it essentially says, every time I see an equal sign for integers, that means copy, right? Every time I see an assignment operator for an integer, that means copy. Strings don't have that subroutine written for them. Strings do not implement this copy trait. Is the technical term that I would say. You can still copy strings. You just have to be explicit about it. There's a special function you call to copy strings, because oftentimes you don't want to be, like if I like assign, like if I have like arbitrarily long strings, I don't want to have to deal with the overhead of like copying all of them. Whereas like ints are like, small and like bite-sized, and like, we can easily copy those around. They fit inside of a register, right? So it's like pretty small. Does that answer your question? So just moving forward. Yeah, okay, so a lot of thoughts y'all are probably having right now. Okay, like especially with like the whole single owner thing, that's dumb, right? Like why, this must make it so hard to write code, especially if we have to return ownership like at the end of every function call, right? So it turns out Rust actually has some ways of like going around this. You can actually take references to data, but you have to be a little bit disciplined about how you do that. And we'll talk about that in the next couple of slides. So yeah, Ryan, do you want to sort of like mention this analogy right here?
Yeah, so as a thought experiment, let's say that you have a group of lawyers, and to map this to code, the lawyers are functions, but you can just think about them as lawyers right now. Let's say that you have a group of lawyers that are trying to sign a contract. They're trying to collaboratively come up with a contract and sign it together. No lawyer would actually do this. Like you'd have one lawyer that kind of prepares things and then sends it, and then they give feedback over email, and they like make adjustments and blah, blah, blah. But let's just say that this is what they're doing. What are some ground rules that we would need in order to make this setup work, in order to make sure that nobody gets gypped? Armin, go back. In order to make sure that nobody gets gypped and like nothing bad happens, what are some restrictions that we need to set on the scenario? Why is that important? Okay, that's very important. And let me expand this and say that instead of just signing the contract together, they can edit the contract. They're trying to come up with the substance of the contract at the same time. So this is a very good point. What else do we need to restrict? Yeah, you definitely don't want it to be the case that like people can be reading the contract and then they get to the end, and when most people are looking at the end of the contract, somebody has snuck up at the top and like changed something around. You want to make sure that while people are reading it, there's nobody editing the contract, right? But we do want it to be possible to edit the contract. That's pretty important. So how would we do that? How would we allow that safely? Yeah, exactly. And the crux here is if there is a single person editing the contract and nobody else is reading it or accessing it in any way, that's fine. And if everybody is reading it, that's also fine, as long as nobody is writing to it. But as soon as somebody is trying to modify, there should only be a single person modifying, and nobody else should be allowed to be reviewing the contract at the time, because there may be some issue where they're like reading one part and they think like everything up to that point is fine, but really somebody has snuck in earlier and changed something around. Does this make sense to people? And to give you an idea of how this maps to code, the lawyers here are really variables, or like pointers, you can imagine. You have multiple pointers to some region of data. And if you are modifying that region of data through one of the pointers, you want to make sure that nobody else is accessing that data through one of the other pointers. Or this is not how Rust thinks about it, but you can think about this in terms of functions. Say that you are modifying the data in one function. You want to make sure that there aren't any other functions that expect that data to be unchanged. This goes back to that dangling pointer example where we had our main function that had a pointer. It called some other function. That function changed the buffer from underneath it and violated the expectations of the main function.
Precisely. And this maps to how like Rust thinks about fun, right? Like I should be able to have many const pointers to a piece of data, right? But if I have a non-const pointer to a piece of data, that can invalidate the other const pointers that are viewing it, right? This would be like one lawyer sort of like writing as other people are like viewing the contract. And then if I have, and I can have at most one non-const pointer at any given time, like that's okay. So the way this manifests itself is that you can have multiple shared references at once. This is called like a shared borrow, right? These are mutable references with no mutable references to that value. Rest will actually enforce this. And you can have only one mutable reference at once and no shared references. And the important thing to remember here is that this will pop up a lot in systems programming in general, especially when you have this concept of like readers and writers. So some of you might be taking 110 right now. Some of you might have already taken it. You will start seeing this concept pop up in CS 110 when we talk about threading and concurrency. If you've already taken CS 110, then you might have heard of something called a read-write lock. That might have been a lab, or I guess like a section question you've done. The other important concept here is there's this idea of lifetimes associated with pieces of data. So the lifetime of a value starts when it's created and it ends the last time that value is used. And the Rust compiler tries to figure out these lifetimes, right? So it doesn't let you have a reference to a value that lasts longer than the value's lifetime. That's exactly the first dangling pointer issue we saw. We had the stack allocated vector and we tried to return a reference to it. The stack allocated vector lives shorter than that reference. That shouldn't be allowed. And then Rust tries to figure out lifetimes at compile time using static analysis. I'm not going to go into too much detail about like how that works, but if you're interested in like more resources, I have like a resources slide at the end. And this is oftentimes like an over approximation. And then once something goes out of that lifetime, it gets deallocated. So there's an automatic drop call inserted. And this is essentially what a destructor is, more or less. Are there any questions about this? Like any like quick questions about this in general? So like this pertains to references because we don't want the references to live longer than the actual pieces of data. Like I don't want to have a reference to a piece of data that's going to become invalid. Does that make sense? Great. So let's actually look at a borrowing example, right? So if I have like, so this is what these borrows actually look like in code. If I want a mutable borrow, I use this ampersand mute thing. And if I have a shared borrow, I use this ampersand string thing, right? 1 second, sorry, let's go back. Okay, I guess you can't see my cursor anymore. But notice how I can have this mutable string, hello, I can call change it up on it and I'll change it to goodbye. And then let me see, we'll take a shared reference to it, right? And it just prints out the string. And then make it plural will take another mutable reference to it. And notice how I have to pass an ampersand mute of s when I'm invoking a function. So notice this is kind of like a weird subtle point. you have this ampersand mute in the ampersand, like it's both in the function definition and in the function invocation. Does that make sense? So this is just sort of like what it looks like syntactically. Because I'm short on time, I'm going to go to the next example. But another thing I wanted to show here is that notice how this push method, it just adds a character to the end of the string. It appends it to the end of the string. And it takes in an ampersand mute to self. So we haven't talked about what self is yet. We'll talk about that on Tuesday probably when we talk about like more object-oriented type Rust. But you have to have this mutable reference passed into push in order for it to work. So yeah, kind of like a subtle thing here is that S is defined as just sort of like a variable. So when I do S dot push, it actually implicitly casts it to an ampersand mute. It's like a weird nuanced thing. We'll actually see that in the next slide as well. So with vectors, it looks like this. This is actually a question that somebody asked me about yesterday. And the issue here was, right, if we have, so can anyone like spot the issue here, actually? I guess we're running low on time, so I'll just tell you the issue. We have let v is equal to vec. So this is a very like well-intentioned piece of code. But the thing in Rust is like when I say let v equals vec, v is by default immutable. C++ on the other hand, by default makes things mutable. It doesn't really care. You have to go out of your way to declare something as constant in C and C++. Here, you have to go out of your way to declare something as mutable. Philosophically, I think this is better because it's much harder to screw up if you make sure that you have to like go out of your way to say like, yes, this is mutable, this can change. And in order to call something like iter mute, if you look at the function signature, it takes an ampersand mute to self. And if I have v as immutable, I can't take that ampersand mute reference. That is why the Rust compiler is complaining. But look at this, the Rust compiler is so helpful. It says, help, consider changing this to be mutable, mute v. Right? Isn't that great? Like, when was the last time you had a compiler tell you what you were probably supposed to do in order to make your code work? That's pretty incredible, right? So the other really cool thing to realize, these are sort of just some parting thoughts. All of the things I just talked about are enforced at compile time, right? And this is a huge deal, right? Because you compile your program only once, but you can execute it as many times as you like afterwards. So shifting things to compile time is actually huge. And this is like this is sort of like what people try to do. Like there's like open research questions about like how many kinds of checks can we just like guarantee at compile time, right? And this is like, to use like economics terms, this is like, we have like a fixed cost investment in our pre-processing in a way. Like if I want to open a pizzeria, I only have to like buy the pizza oven once and I can make as many pizzas as I want, right? I only have to compile my program once and I can compile it as many times, I can run the executable as many times as I like. So in general, you want to do this shift, right? So oftentimes there's like this tension between security and performance, right? And Rust tries to give you both. Just don't screw up what you're doing in your compiler, the checks you're making in your compiler, because there are a lot of security vulnerabilities that pop up from making fancy optimizations. But there's been a lot of like vetting done of like the Rust compiler, and it's like developed by experts, and like in general, you can like trust like the changes they're making. I think there's like a good amount of research on also like verifying like certain aspects of like what Rust does. But that being said, there have been vulnerabilities in Rust. Rust is not like a panacea. It's not perfect, right? Yeah, and just kind of like as a reminder, like for the first assignment, we just want you to get familiar with the basic syntax. You'll definitely see ownership and borrowing in action, as many of y'all already have as you've tried to decompose your code. Please ask questions on Slack. And if you feel comfortable, please ask them in like the public channel so that other people can benefit from the answers as well. And I guess like before you ask the question, like see if like someone else has already asked it. Yeah, sometimes like it might be hard because you don't want to show your code. So you don't have to show your code explicitly, but if you can type up a code example and ask questions about that code example, that's completely fine. Does that make sense to everyone? And like feel free to like chime in and like help each other out too. And if you're interested in additional resources, that's on the last slide. We'll post these slides soon. Shout out to Will Crichton for providing some feedback on how to explain some of these concepts. And thank you all so much for coming, and feel free to stick around if you have questions.